Yeah, good afternoon. Thank you very much for the invitation and for the introduction. I think I only understood a few words, but they were correct. So it's a great pleasure to be here in this famous university, and I'm very glad that I have the opportunity to give this lecture, which will cover quite some ground. I hope it will be okay, but we'll see how we get it going on. So what I'm going to talk about is some recent developments in condensed matter physics, and as it's called nowadays, quantum matter. Quantum matter is matter that is influenced very much by quantum mechanics, collective quantum effects of all kinds. And you will see at the end that there are many such effects. So here's the outline of my talk. We'll mostly be talking about electrons in metals. And electrons in metals were actually the first instance of quantum matter to be discussed in physics. Already in the 1920s, when quantum mechanics had been invented. A very important framework for the description of quantum matter is the idea of quasi-particles. The idea that low-lying excitations in these systems can be described by a few particle-like excitations. And as we go along, it will be interesting to see how these quasi-particles change when we come to more complicated situations. And I'll discuss several of these more complicated situations, like ordered states, which are relatively well known since a long time. What happens to the quasi-particles in ordered states? That's our first topic, and it's just kind of a recapitulation of what we all have known for a long time and what we are working with. Then we'll go on to the first relatively new subject, and that is what happens to quasi-particles near quantum critical points. Quantum critical points are phase transitions at zero temperature. So you would say, well, zero temperature is not accessible anyway, so how are we interested in quantum in a phase transition at zero temperature? But as I will show you, the influence of this quantum critical point at zero temperature, at finite temperature, is tremendous. And there are really big effects, and it's an absolutely new big field of research nowadays. Then we'll talk about the next example, frustrated quantum magnets, where I will discuss that the usual excitations in quantum magnets, which are quantized spin waves, break up into fractional quasi-particles, namely spin-ons. At least that's the prediction. We'll talk about how this can be reached experimentally. Then I'll talk about quantum wires, and this is close to the collaboration I've had for many years with Professor Dmitry Arizkov here, where we'll show how the fractionalization of the charge part of the quasi-particles, the so-called charges, leads to interesting effects in the conductance of quantum wires as a function of temperature or as a function of voltage. Then we'll enter a field that came into existence in the 1980s, but was theoretically understood only much later, namely electrons in two dimensions in a strong magnetic field, the quantum Hall effect. And there especially the fractional quantum Hall effect, where new quasi-particles appear, composite fermions, or the Volfle quasi-particles. They are, in my view, the most exotic quasi-particles that we know so far. And very recently, only a few years ago, the subject of topological insulators came into existence. This is basically a further development starting from the quantum Hall effect, and we'll discuss how in these systems another type of particle, namely Majorana fermions, will be accessible experimentally. It's not so 100% clear now, but I'll explain how one can devise systems that should show Majorana fermions. Then I'll conclude with summary and outlook. Okay, electrons in metals. The first example of quantum matter, as you all know. The interesting part in the metal is the conduction electrons. And the physics of the conduction electrons was not understood at all before quantum mechanics was invented. But shortly after the formulation of quantum mechanics, Sommerfeld had a wonderful model for electrons in metals, namely he tried to model them by a Fermi gas, a non-interacting Fermi system. And as you know, the particles, the electrons in a solid are quantized in momentum eigenstates. So they occupy being fermions. One fermion occupies one state. So we get to this situation that in momentum space, the Fermi sphere is occupied, and the weakly excited excitations are particle hole pairs close to the Fermi surface. Now, if you have an energy temperature at our disposal, and the temperature is much less than the Fermi temperature, then we know that only a fraction of T over Tf of the particles are excited, and then we can immediately say what the specific heat will be. Classically, the specific heat is constant, and now we have to multiply this by the fraction T over Tf, so the specific heat will be a linear function of temperature, and the spin susceptibility or magnetic susceptibility classically is 1 over temperature, Curie law, and multiplying by T over Tf will have a constant, here, Pauli susceptibility. Okay, so we have to add to this very, very simple model the consequences of the periodic potential, which is formed by the ions, and this has been done by Bloch, and then you get the band structure of the energy spectrum of electrons in the crystalline solid. Up to now, this is a completely non-interacting model, and this model is not good enough to really describe solids. So one has to take into account the interaction between electrons in some way. And a very, very powerful, unfortunately not exact way of doing this has been invented by Kohn and collaborators in the form of the density functional theory. So I don't have time to go into this, but it's a very well developed theory. It's sometimes called ab initio, but ab initio with some limitations. But if it works, if you have not too strong electron-electron interaction effects, then it works very, very well, and you can actually calculate the properties of solids from scratch using this method. This is the one-particle theory of electrons in solids, and it's the starting point for all description of solids nowadays. However, what we should keep in mind that it's actually a miracle why such a theory should work. Because there's electron-electron interaction. And as we know, for the distances of electrons in a metal, the electron-electron interaction is on the scale of several electron volts. So it's a huge interaction. So why does such a simple one-particle theory work at all? Now this has been solved by Landau in the 1950s, and he got the Nobel Prize for that. Namely, Landau had this beautiful picture that if you imagine to start with a non-interacting system, free electrons, and you switch on the interaction between electrons adiabatically, and what's happening is that this electron will be surrounded by a cloud of particle Hall excitations and will form a particle-like object, a quasi-particle, a Landau quasi-particle. Why is that a useful concept? Well, the Landau quasi-particles are not exact excitations. They decay. But if the decay rate, gamma, or the inverse decay time, 1/tau, is much less than the energy of the particle, this particle is well defined over a sufficiently long time, and we can work with it. And in the original formulation, this decay rate is proportional to the energy squared. So if you compare energy squared with energy, in the limit energy going to 0, energy squared will of course be much less than energy. So these particles are very useful. And this Landau quasi-particle has all the quantum numbers of the free particle. And the effect of interaction is absorbed in a few parameters under the effective mass and star that will play a big role later on, and the Landau parameters that describe the interaction, the remaining interaction of the quasi-particle. So most of the interaction between the electrons is absorbed into the effective mass and into the effective interaction parameters, the Landau parameters. But a little bit is left. And this is described by the Landau parameters. The best way of visualizing the quasi-particle is to look at the single particle spectral function. So this is a single particle spectral function as a function of energy. For non-interacting electrons, it's of course a delta function at the energy EP of the particle. If you switch on the interaction, this delta function will be broadened, and the width will be gamma, just the same gamma I discussed before, and the weight will be decreased. The weight we call Z, capital Z, and in many cases, the effective mass of the quasi-particle, the effective mass ratio is equal to 1/Z. So if the weight under the quasi-particle peak shrinks, the effective mass will increase. And in addition, there's an incoherent background about which we know little to say. It's very hard to calculate, but once we have the quasi-particle peak here, we can calculate all the properties of the system that depend on the low energy excitations without saying much about the incoherent background. Because we will later come to a situation where the decay of the Landau quasi-particle is much stronger than what I discussed so far. Let me say here that what is required for the Fermi liquid idea to be applicable is that the quasi-particle weight is non-zero. That's clear. We have to have a peak here. And that the quasi-particles establish their energy before they decay, so that gamma should be less than the renormalized energy. If that's the case, we have quasi-particles, and we can work with the quasi-particles, even if these quasi-particles are no longer the old Landau quasi-particles, but we are in what's called a non-Fermi liquid regime. Okay, but that's good to keep in mind. So the quasi-particle picture of normal quantum matter is a model description of weakly excited states, of weakly excited, strongly interacting systems, by mapping onto a system of nearly free quasi-particles, which are fermions, Landau quasi-particles, or a zoo of bosons, zero sound, which is a sound wave, phonons, plasmons, excitons. We only need to calculate these quasi-particles, and then we can evaluate all the observable quantities. However, if the Landau Fermi-liquid interaction is strong enough in some way. There are infinitely many channels. This can happen. But if it's strong enough in one channel, the system will become unstable and it will go into a ordered state. And the question is now, what happens to these quasi-particles, sort of the really fundamental entities, when we enter an ordered state? Okay? Actually, the system for which Landau developed his theory was not electrons and metals in the first place, but it was the quantum liquid helium-3. And it's interesting to have a look at the experimental properties of helium-3. So if you look here at the effective mass ratio goes from 3 to 6 as the pressure is increased from 0 ambient pressure to 30 bars. So it's a very strongly enhanced effective mass. The compressibility, which is given in Fermi-liquid theory by effective mass ratio over 1 plus a Landau parameter F0S for spin symmetric, is decreasing with pressure. Now, since m star by m is increasing, F0S has to increase even more in order to overcompensate the increase here. And this F0S is as large as 20 or so at large pressure. So it's an enormous interaction. Strong coupling. Whereas the spin susceptibility follows the m star by m roughly, so that F0A is approximately constant and it's around minus 3 quarters. Now these dependencies can be very well understood in a simple model I just want to mention, namely in the so-called Gutzwiller approximation. So if you describe helium-3 as a lattice gas, and you say, okay, on each lattice side there can be either one atom, or if there's a second atom, then there's a large interaction energy, U, you should call U. If you use this model and you calculate in the Gutzwiller approximation, you get exactly this behavior. So this is relatively well understood. What I want to come to next is that in helium-3, although it is a Fermi liquid over a large portion of the phase space, so this is pressure versus temperature. So this is the Fermi liquid part here. This is classical liquid gas, solid here. At some very, very low temperature, millikelvin, the system undergoes a phase transition into a superfluid state, an ordered state. So this is interesting, and let's look at that. What is it? Okay, of course a Fermi system cannot become superfluid like a Bose system can. Bose system, of course, condenses into Bose condensate, and the Bose condensate will be superfluid. But what a Fermi system can do is that it transforms the fermions into bosons, in some sense, and the bosons condense. And this is the case if the fermions form pairs. Pair is a boson, of course. Two fermions are a boson. And that's what happens in superconductors. And the same happens in helium-3. So superconductors were explained by the BCS theory in 1957. And the same idea was applied to helium-3, where the superfluidity was discovered later, in 1971. And so you imagine that you have the two partners of the Cooper pair, two helium-3 atoms, and they form a pair. And the difference, or I should say the only difference, not much difference, of a Cooper pair in helium-3 and a Cooper pair in a superconductor is that in a superconductor the electrons form a S-wave state pair. S-wave means that the partners of this pair come close to each other. When you remember S-wave wave function. That is not allowed in helium-3, because the helium-3 atoms have an interaction potential that is strongly repulsive at short distances and attractive only at intermediate distances. So that tells you that the Cooper pairs have to be in a finite orbital angular momentum state. And it turns out to be L equals 1. And if it's L equal 1 or any other odd L state, because of the Pauli principle, it has to be spin 1. It has to be a spin triplet state, which is a big step in complication from Cooper pairs in a superconductor, which is S-wave and spin singlet, to this case, because such a state here has 3 times 3 substates. So we have not only one order parameter, a complex number, but we have a matrix, an order parameter matrix, 3 by 3 matrix. So you would expect that there are several possible phases, and that's exactly what is seen here on this plot here. There are 2 phases, A phase and B phase, and there are some more phases in the finite magnetic field or near a boundary and so on. So what's the difference between these 2 phases? Well, the probably most direct difference is that in the B phase, the energy spectrum acquires a gap that is isotropic all around the Fermi surface, whereas in the A phase, the gap function has nodes here along some vector L. Okay, so that's already one of the properties of the fermionic excitations. I said I wanted to discuss what happens to the quasi-particle excitations in an ordered state. And this is what happens. Then the Landau quasi-particles, they die, and they are reborn as Bogoliubov quasi-particles. The Bogoliubov quasi-particles, their number is no longer conserved. So there is no longer a one-to-one correspondence between electrons and Bogoliubov quasi-particles. And the energy spectrum acquires a gap. Of course, the reason why this is so is that 2 quasi-particles can merge into a Cooper pair or the opposite. Okay, what about the bosonic sector? Well, it's actually quite interesting. The elasticity of the order parameter field. So imagine we have this order parameter field, which is this expectation value of the pair operator here. So imagine to have this order parameter field in space and time. Of course, in the ground state, or in the equilibrium state, this will be a spatially uniform and time-independent order parameter field. But if you disturb this order parameter field at some position, what will happen? Well, the order parameter wants to go back to its equilibrium value, which means it's an elastic medium. This elastic medium can sustain various types of oscillations. There are acoustical oscillations, so-called Goldstone modes, which are related to the broken symmetry of the state. And they have either dispersion omega proportional to k or similar, so-called Anderson-Bogoliubov sound mode, which is the transform zero sound, spin waves, orbital waves. But if the Cooper pair has internal structure, there can also be optical modes, which means so-called massive modes, modes which have a finite energy in the limit k momentum going to 0, also known as pair vibration modes. So we have new bosonic quasi-particles, and in addition, we have another possibility to generate a type of quasi-particle. That is, if you can have defects in the order parameter field representing localized quasi-particles. They are usually protected by topological constraints. So we can have domain walls, vortices, and so on. I find one of these pair vibration modes to be most spectacular in the system. That's I want to discuss it briefly. Namely, in the A phase, the order parameter matrix has this form. There are two vectors n and m in orbital space, and there's one vector d in spin space. So the vector d is, for this purposes, is not important, but n and m are important, and n and m are perpendicular. So you have a vector n, you have a vector m, and actually perpendicular to these two vectors is the vector L, which describes the orientation of the gap nodes. Okay, so now you can imagine, this is a 90-degree angle in equilibrium. Now you can imagine that this object, which is kind of a molecule, can have vibrations of at least two types. One is what is called clapping. This is when these two n and m vectors move against each other. And the other one is flapping, when n and m move against L. Okay, these modes can be calculated. This is what I did a long time ago, and one finds that the frequency of these modes is a function of temperature here, plotted in this way to make it have a better representation. So the frequencies are for the flapping mode this, for the clapping mode this, but there's another flapping mode, super flapping, which is however damped, overdamped, so it's not so important. And now imagine you send ultrasound into the system. If the ultrasound couples to these modes, then you will see a peak in the sound absorption. And this is exactly what happens. So if you have ultrasound of this frequency here, it will cut these collective mode frequencies in all these places here circled. And in these places you should find a peak. And this is what is seen here. Ultrasound absorption is a function of temperature. Unfortunately, it's a little bit different representation here, but you can believe me that exactly at the points where we have these peaks here, we have exactly this one, and this one. So that works beautifully. So imagine you have these Cooper pairs, and there are many of them, and they all do the same thing. In the whole system, they all do this clapping mode, you know, like one giant molecule. That's quantum mechanics. Okay. In more recent times, the Fermi liquid theory has had some culmination point when it was applied to the so-called heavy fermion compounds. So heavy fermion compounds, or heavy electron metals, have extremely largely enhanced effective mass ratios, up to 1,000 times enhanced. And then you can see in the specific heat coefficient, C over T, is proportional to the effective mass ratio. And for this compound here, cerium copper 6, this will be approximately constant here at low temperature. And this is the susceptibility magnetization of a magnetic field. It's also approximately constant here. The same happens with the terbium rhodium to silicon 2, where at finite magnetic field you have this constant behavior here. And as the magnetic field is lower, much lower here, when you see something else, which we will discuss shortly. So these are beautiful Fermi liquids with an effective mass enhancement of up to a factor of 1,000. And this is very, very, very convenient if you have this, because it means that the electronic properties are much, much more enhanced in experiment as compared to the phonons. So if you measure the specific heat, for instance, then, you know, in condensed matter, it's not so easy to extract the electronic part, because it will be masked by the lattice vibration part. And this, in this case, is not the case, because we have this enormous enhancement factor. Now you may ask, how does it come about? Where can we get such a big enhancement of the effective mass? It's not an effect of the band structure, of the electronic band structure. It's not an effect of the periodic potential doing something strange, and that causes, this enormously enhanced effective mass. It's a dynamical many-body effect that leads to this. And this is the Kondo effect. And what is the Kondo effect? Well, first we have to talk about what we have in the systems. So these are metallic compounds containing localized spins. So either in cerium, in deuterium, or in uranium, it's F electron spins, or in iron and cobalt, it's D electron spins. And these spins are coupled, as I said, so you have a local spin here, and it's coupled to electrons that are surrounding it by a coupling constant J, so this is the Hamiltonian for this effect. And then something drastic happens. Namely, this local spin at low energy or low temperature forms a cloud of conduction electron spins which screen the local spin completely. So there's nothing left of the spin, there's no magnetic moment left. And the screening is done in a resonance state, a many-body resonance state, Kondo resonance. And if you have a resonance state here, imagine you have this resonance state and another electron comes along, it will get caught by the resonance. It will stay in the resonance for a time that's given by the inverse of the width of the resonance. And the width of the resonance is the so-called Kondo temperature. So it will stay there for a long time and then it will move on. Okay, now imagine the electron comes on, stays a long time and moves on. It looks like the electron would have a large effective mass. It looks like it would move slowly because it has a large effective mass. And this effective mass enhancement is T Fermi temperature, 10,000 Kelvin over Kondo temperature. So if the Kondo temperature is 10 Kelvin, which is a usual number for the compounds I will be talking about later, then we have 10,000 over 10 is 1,000. So then this would be 1,000. It's exactly what we need to explain the properties of these compounds, just mentioned. Okay? So in these compounds, you do not only have one Kondo impurity, but you have a Kondo impurity on each lattice side. So what you get is coherently scattered electrons. So the electron moves along and it goes from resonance to resonance, which makes it clear that it will be trapped, and so on. It will be slowed down by this factor, and it will form a heavy Fermi liquid, below a certain temperature, T coherent, that is roughly of the order of T Kondo. Okay, now, as with any Fermi liquid, this Fermi liquid also has Fermi liquid interaction. And the most important Fermi liquid interaction here is the magnetic interaction. And this magnetic interaction is mostly antiferromagnetic, not always. So this exchange interaction, it will lead to an ordered state. And this is seen here when cerium copper 6 is doped with gold. There are many compounds of this type. I'm concentrating on two of them. Doped with gold. Then we go from x equals 0, which is here. So here we have no magnetic order. We dope here. We get magnetic order here. And this is the Néel temperature for the antiferromagnetic order. And now you see that this Néel temperature is decreasing with doping, decreasing doping, until it vanishes at some point. And this is the point we will be concentrating on. This is a quantum phase transition. It's a phase transition between the antiferromagnetic ordered phase and the not ordered phase. And this phase transition happens at 0 temperature. Before we do that, let's have a look at the quasi-particle excitations in the antiferromagnetically ordered state. So in this state we have an order parameter which is differentially modulated magnetic field of a certain wave vector capital Q, which is often just a lattice wave vector, but need not be, can be an ecometric wave vector as well. So in this magnetically ordered state, say spin up, down, up, down, up, down, we can have spin waves, and the spin waves in the antiferromagnet have a linear dispersion relation, so these are the new quasi-particles that we get in the ordered state. And what happens to the lambda-out quasi-particles? Well, they are transformed to quasi-particles which have now no longer a conserved spin, because these particles can now scatter off transverse spin waves. They can change their spin. So there's no one-to-one correspondence between electrons and these quasi-particles anymore. And they acquire a gap in the energy spectrum as well. This is very similar to the superconducting or superfluid case. So this concludes kind of the introduction, which is what I would like to call the standard model of an interacting Fermi system. Namely, it is Fermi liquid theory plus the spontaneous symmetry breaking, which is one of the most successful concepts in condensed matter theory, condensed matter physics, and it is of course the first thing to apply whenever there is something new discovered, and every year there are new discoveries in condensed matter physics. There are new superconductors are found, and new magnetic states. So the first thing to do is to apply this theory. But sometimes this theory does not work. Now we come to the main part of the talk, namely, this theory stops working when quantum fluctuations, for instance at a quantum critical point, destroy the lambda quasi-particles and destroy the long-range order, of course. And as I explained before, the heavy fermion compounds are very well suited for studying this effect because the electronic properties are enhanced and they are much more easily observable experimentally. So what we have then is, as I already explained in the case of cerium copper 6 doped with gold, is that the antiferromagnetic state disappears at some point here at some concentration of gold. And we have a phase transition here at 0 temperature, or in this case over here, which is ytterbium, rhodium to silicon 2. We have a phase transition as a function of applied magnetic field. As some relatively small magnetic field, antiferromagnetic phase, and Fermi liquid phase over here. So typically, the phase diagram looks like so. We have the temperature control parameter phase diagram has an ordered phase, a disordered phase separated by the quantum critical point, and a huge area here above the quantum critical point where the properties of the system are not like Fermi liquid. They are like a non-Fermi liquid. Non-Fermi liquid is not a nice name because it doesn't tell you much except that it's not a Fermi liquid. But it's in the literature. So up here we get fractional power laws in temperature, fractional power laws in the control parameter, and so on. And this is what we would like to describe. Now, in this compound, it is known from neutron scattering that it shows quasi-two-dimensional antiferromagnetic fluctuations. This is what we will be using later to apply our theory. Over here, we have 3D ferromagnetic fluctuations in the upper part and 3D antiferromagnetic fluctuations in the lower part, at lower temperature. So what happens to the quasi-particles near the quantum critical point? Well, in the Fermi liquid regime, the decay rate of the quasi-particles, which is omega squared, takes up a prefactor correlation length. So in this case, antiferromagnetic correlation length to a power z. Z is the so-called dynamical critical exponent. And psi goes to 0 at the quantum, goes to infinity at the quantum critical point, so this prefactor diverges. At the same time, the quasi-particle weight factor goes to 0. So this is a situation in the Fermi liquid phase when you approach the quantum critical point from here. In the quantum critical regime, which is the middle part here, as I will show, the decay rate is always proportional to omega. It's a linear function of omega. And the weight factor goes to 0 with some power of omega. So the non-bound quasi-particles disappear and we have non-Fermi liquid behavior. So this behavior is shown experimentally in this measurement of the specific heat coefficient. So specific heat over temperature versus temperature here. This is zero magnetic field, this is for this compound I showed you, and you see that counter temperature is roughly here. So you see that below the counter temperature, this quantity, which is supposed to be temperature independent in Fermi liquid theory, starts to rise logarithmically, and at lower temperatures below, when the three-dimensional antiferromagnetic fluctuation set in, as I said, it starts to shoot up with a power law behavior. This is what we like to explain. Now there is a very old idea that has been formulated by Doniak's hypothesis in the 1970s. That goes like, so we have the Fermi liquid conduction electrons, we have the localized spins here, we have the Kondo coupling. This will produce an energy scale T Kondo. Okay. But we also have the possibility of interaction of the localized spins by this process, so exchange process going up to the conduction electrons and coming down here. And this is the so-called RKKY, Ruderman-Kittel-Kasuga-Yoshida interaction that's proportional to the exchange complement squared. So in one domain, which is over here, this one will dominate, and then we would say, okay, the interaction between the spins dominates, and we'll get antiferromagnetically ordered state. And over here, when T Kondo dominates, we'll say, okay, the Kondo effect will take place, and the magnetic moments will be removed by the Kondo effect before the magnetic ordering can ever happen. And the question is what happens in between. Then these people say that the Kondo effect breaks down, which would tell you that if the Kondo effect breaks down, that the effective mass enhancement would have to disappear as you go to this direction toward the critical point. And once you are here, you have well-established, localized moments that interact. So you would expect magnetic moments of the order of unity in experiment, right? But this is not the case. Experimentally, one does not see that the effective mass is decreasing on moving to this antiferromagnetic order state. It's still large. It's almost unchanged. The observed magnetic moments in the ordered state are small. They are only percent of the total moment of a mu Bohr. And a convincing sign of an abrupt change of the Fermi volume, namely a Fermi volume which is large, which contains the spin part, the localized spin contribution, to a small Fermi volume where the localized spins are removed. That is also absent, although people have claimed that such a transition can be seen, but I disagree. Instead, our own theory focuses on the effect effects of the scattering of heavy quasiparticles by critical spin and energy fluctuations. Well, I explained why energy. And the changes in the spin and energy fluctuation spectrum induced by the critical quasiparticles. So these two things have to be taken together. So we have to look at what happens to the quasiparticles when they scatter critically, and we have to look what happens to the spin fluctuations when the quasiparticles become critical. And there's a balance between these two systems, the spin fluctuations and the quasiparticles. And this will lead to a self-consistent strong coupling theory of the quasiparticle effective mass, which has all the properties that are observed, hyperscaling, fractional power laws, and we get excellent agreement with experiment. Before I go into this a little bit, sketch what we have been doing, let me just make one point. I said before that for the quasiparticles to exist, it's enough that there is a peak so that the quasiparticle weight is non-zero and that the width or decay rate of the quasiparticles is less than the energy. Okay? Now surprisingly, it turns out that this is the case if you have an even extreme frequency dependence of the self-energy. So the quasiparticle weight is given by this expression, so it's 1 minus the frequency or energy derivative of the self-energy. And if you assume that the self-energy has a power law dependence with a very low power here, then the weight factor is proportional to omega to this power eta. The quasiparticle width or decay rate is defined as weight factor times imaginary part of sigma. That's always linear, as I said before. If it's linear omega, then the question is, what is the prefactor here? Okay? So you can calculate this prefactor and you find that they're both linear. Gamma is, of course, linear and E is omega anyway. So what is this number? Is this number less than 1 or is it larger than 1? And it turns out that for values of the exponent between 0 and 1/2, this factor is less than 1, and the quasiparticle width is less than the energy, and we have quasiparticles. Okay, you can see that here there are lots of the spectral function for these different values of eta, and you see there's a nice quasiparticle peak. No problem. Okay, so what we do then is we have to model the spin fluctuation spectrum. So this is the dynamical spin susceptibility as a function of wave vector and energy. It's given by the density of states over a denominator that is the control parameter R, which is magnetic field or concentration of gold in this case and so on. It has a momentum-dependent part, which is momentum minus the ordinary momentum squared for the antiferromagnet. And most importantly, there is an imaginary part, which is the so-called Landau damping. The spin fluctuation may decay into particle-hole pairs. And this is described by this Landau damping part here. And the important ingredient now in our new theory is that this Landau damping receives a correction factor, which is a vertex correction squared, and this vertex correction is proportional to m star over m. It goes to infinity when m star goes to infinity. So this is critically enhanced here. Okay? How do we calculate the self-energy? Well, we calculate it with this so-called rainbow diagram, one loop diagram. So this is the spin fluctuation propagator, this is the Green's function for the electron, these are the vertex corrections again. So from this we get sigma of omega, and from sigma of omega we get m star over n. Now there's a little complication here, namely if you look at this, and this has been studied already 20 years ago, then one observes that this process is only possible at special sites of the Fermi surface, namely the so-called hot lines. So in 3 dimensions, hot lines. So this red lines are the hot lines. Why are they so special? Well, they are special because they are connected by momentum Q, ordering wave vector. So if you have a quasi-particle here, and it absorbs or emits a spin fluctuation of momentum Q, it will end up here. It will also be on the Fermi surface. If you take any other state like here, and you do the same thing, you end up at a point that's way outside the Fermi surface. And such a state is not renormalized because it's an off-shell state. Okay. So that tells you that from this diagram you get a very strongly K-dependent self-energy. Experimentally, there's no sign of this K-dependence. Experimentally, it looks like the self-energy is completely K-independent. How can we get that? Well, there are two ways to get it. Then you can have impurity scattering, which distributes these hot lines all over the Fermi surface. That would mean that the critical parts that you calculate are proportional to some power of the impurity concentration. So they should be different for different samples of different impurity content. But this is apparently not the case. So we have to look for another possibility, and that is actually a so-called two-loop approximation. Then we exchange of two of the spin fluctuation propagators, one with plus Q and one with minus Q, so that the total momentum exchange is zero. And this is actually something like the exchange energy propagator. So it's like an energy fluctuation here, and if we calculate things, then we get an interesting result. And with the effective mass that we get from here is given by 1 plus a expression that has some power of energy here, which is E minus 3/2. And it has a prefactor that that's some power of m star. Actually high power of m star. T is the dimension. Now, if you are in 3 dimensions, then we have 3 minus 3/2 and 3/2. E to the 3/2 would go to 0, and the energy goes to 0. So if this effective mass is never large, then this term would just go to 0 as the energy goes to 0, and nothing much would happen. And this is actually also seen in some of these compounds. This is called a spin density wave transition. This is a transition into a sort of normal so-called weak coupling spin density wave state. If, however, m star is large already, and I can tell you in this one case it's large because of the ferromagnetic spin fluctuations, then this prefactor is already large. And you start with a initial condition where this term is larger than 1. And you can drop the 1 here, and you get a self-consistent equation with a new solution, a strong coupling solution, and it turns out that m star is then a diverging function, e to the minus 1/4 in 3 dimensions, and e to the minus 1/8 in 2 dimensions. And this is what describes experiment very well. So, what do we get? I show you only a selection of this comparison, but I can only say that all the quantities that have been measured and where we were able to make comparison with were very well explained by this theory. So we would predict that the specific heat coefficient C over T diverges as temperature to the minus 1/4. And this is the fit to the experimental data, and you see it's a perfect fit. We would say that outside of the critical cone, so if you approach the quantum critical point from the Fermi side here, as a function of magnetic field, they find experimentally an exponent of minus 1/3, and we have minus 1/3. In the other system, namely cerium copper doped with gold, At the critical doping of 0.1, we predict a dynamical structure factor S of Q and E as a function of temperature of this form. So N is the Bose function here. So you see that there is a critical exponent 3/4 here. And this is the fit of this function to the experiment, and it's a very good fit. And actually, before our theory was even formulated, the experimentalists were fitting their data with a fractional power law, which was 3/4. Okay, so this concludes the section on critical quasi-particles near a quantum critical point. Okay. Let me now come to the next point, namely a situation in a non-metallic magnetic system where the usual correlations are destroyed by frustration. And what happens then is that the spin 1 excitations, the spin waves, may break up into spin 1/2 particles, quasi-particles, so-called spin-ons. This is a relatively elusive thing, I have to say. And spin liquid state has been postulated a long time ago, and it has been sought after in many different systems, and so far it has not really been established well. But there is a new chapter in this story that was opened a few years ago, and since we have done calculations in such systems, I want to show you that. So let's start with the simplest possible system. This is a so-called J1, J2 Heisenberg model. So we have a Heisenberg model with the nearest neighbor interaction J1 and next nearest neighbor interaction J2 on a square lattice. We define the ratio J2 over J1 as G. Then what has been found in numerical studies is that for small g, when the nearest neighbor interaction dominates, you get the usual antiferromagnetic state, up, down, up, down, up, down, and so on. When the next nearest neighbor term dominates, you get a so-called collinear magnetic state, where you have rows of up